Today we'll be studying Ohm's law and resistance. The resistance R is defined as the ratio of the voltage to the current that goes through a material. The figure to the right is called a circuit. It is used to model and simplify the actual device. So let's look at this circuit. We have a battery, and following conventional current goes through the resistor, through a switch, and then back, which is the same thing that actually happens here in the actual device. You have the battery, it goes through the resistor, back, through the switch, to the other side of the battery. So what is Ohm's law? It occurs when the ratio of V over I is a constant, where we know that V is the voltage applied across the material, and I is the current that goes through the material. So in other words, when V over I ends up being a constant, the object obeys Ohm's law. So if we assume something obeys Ohm's law, we can actually take this equation and solve for other terms such as V. Like in other words, voltage is equal to current times resistance. And the unit for resistance is volts per amp, which is commonly called an ohm. To the extent that a wire or an electrical device offers resistance, it's called a resistor. So sometimes we put resistors in circuits to limit the current that goes through them. So here's an example. A filament in a light bulb is a resistor in the form of a thin piece of wire. The wire becomes hot enough to emit light because of the current that goes through it. The flashlight uses two 1.5 volt batteries to provide current of 0.4 amps to the filament. Determine the resistance. So we're going to use Ohm's law to do this. So we know that Ohm's law is V over I is equal to R, but it's more commonly seen in this form, that current is equal to voltage divided by the resistance. So if we solve this for resistance, we take the voltage divided by the current, we have how many ohms it is. So this filament offered 7.5 ohms of resistance. Now, there's an analogy that's used with simple circuits that really helps you understand the whole idea between like current, resistance, and voltage. And that analogy is a water pump analogy. And I took this from this website here. I just wanted to give them credit for that. So here's the analogy we're using. We'll be talking about it. Okay, a water loop with a pump is a common analogy for electric circuits, like I just said. The water flow rate, how much water in gallons per minute that go through it, is the same thing as like the charge that goes through this, or the current that goes through the circuit. The pump increases pressure of the water, so the pressure goes from the high point of the pump through the device and through the low point of the pump. Analogous to that is the battery increases the EMF, or the pressure per unit charge, or the energy per unit charge. The more pressure the pump provides, the more water that flows. The more voltage or more EMF, the more the current that flows. In this situation here, we have some type of constriction device that slows down the water. Resistors do the same thing. It flows the current down. More restriction, less water flow. More resistance, less current flow. And here's another important idea. All the water that left the pump comes back to the pump, but at a lower pressure. So let's say there's 100 psi here and 0 here. So it lost all of its pressure going through. And the same thing can be thought of with the electric circuit. It starts here at high EMF, and it goes through and loses all its voltage by the time it gets back to the battery. All right, for a wide range of materials, the resistance of a piece of material of length L and cross-sectional area is given by this equation, where rho is the resistivity, and that's measured in ohm meters. So we can take a whole bunch of different materials, look at the resistivity and their physical makeup, like what their length is and what their area is, and determine the actual resistance that they'll provide to the circuit. So if we know the resistivity, we know the length of it, and the cross-sectional area, we can find the actual resistance. So here's an example. The instructions for electric lawnmower suggest that a 20 gauge extension cord can be used for distances up to 35 meters, but a thicker 16 gauge cord should be used for longer distances. And this should make sense to you because as you go a longer distance, according to that equation, you can have more and more resistance. So by using a thicker gauge, you go from 20 to 16. 16 is actually thicker. You offer more area, so there should be less resistance. So what we want to know is, what is the resistance of these two extension cords? So we just use the equation. So here's the first one. The resistivity is the same. I got this number from that chart. I know the length and I know the area that was given to me right here. So that's the resistance of the first electric cord. Now you go to a heavier gauge, still the same resistivity because it's still copper, a larger length, but the area helps you out, and there's even less resistance than the smaller cord. Okay? So that's the idea of Ohm's law and resistance and resistivity.